Hi everyone, in this video we're going to look at a particle sitting on top of a rotating saddle and consider how the particle is going to move over time and how its motion depends on how quickly the saddle is spinning around. So we'll end up deriving a couple of results that I think are very cool but also very intuitive. Now, to start making some progress on this, the first thing we're going to have to do is come up with a mathematical description of our saddle shape. And in order to do that, we've got to put a coordinate system down. So I've got a diagram of a saddle shape here. I've drawn the particle just sitting right in the center there. I'm going to define the center of the saddle to be the origin of the coordinate system. So if I just draw three coordinate axes going that way and that way, and then pointing straight up. And in order to keep this a right-handed coordinate system, I'm going to say that one's going to be x, this one is going to be y, and z is going to point straight upwards. So the simplest type of saddle shape that we can define basically looks like a parabola in the x direction, an upwards curving parabola in the x direction, and then just a downwards curving parabola in the y direction. And so if we combine those two facts together, we can describe a saddle shape, the surface of a saddle shape, by the following equation. Z is just proportional to x squared minus y squared. Right? Now, this is very useful because this allows us to make a link to the dynamics of the particle. Because if you think about it, the potential energy of the particle, which I'm going to call U, is just gravitational potential energy, which is just its mass times the field strength times its height, which is just Z. Right? So if Z is described by this x squared minus y squared function, but the potential energy is just mg times Z, we can also conclude that the potential energy is proportional to x squared minus y squared. Okay, so I'm now just going to put in a constant of proportionality into that relationship there. So I'm going to say let u be equal to, now I'm going to explain this choice of constant of proportionality in a second. For now, I'm just going to call it half m omega squared, where m is the mass and omega is just some constant, times x squared minus y squared. Now, the reason for choosing this particular combination of parameters rather than just calling it like k or something is that it makes the equations of motion work out very nicely, right? So if you forget about the fact that the saddle is rotating for a second and just imagine a particle moving on a stationary saddle, right? The equation of motion in the x direction would, from Newton's second law, would be m times the second time derivative of x, in other words, mass times acceleration, is going to be the force in the x direction, but the force in the x direction is minus the partial derivative of potential energy with respect to x. And then we would get a very similar equation in the y direction. My double dot, where a dot is a time derivative, is minus partial du by dy. Okay, now if we plug in our u function into those partial derivatives and rearrange the equations, we find that in the x direction we get x double dot plus omega squared x equals 0. And this is just a simple harmonic motion equation, right, which has a solution x being proportional to e to the plus or minus I omega t, right? So x kind of oscillates as you'd expect. It's just the same as like a mass on a spring, right? It's in a quadratic potential. In the y direction, the only difference is the minus sign, and so you end up getting y double dot minus omega squared x is equal to 0. And the solutions to that are of the form y proportional to just e to the plus or minus omega t. So we don't get an I this time. Okay, so this is essentially the justification for choosing my constant of proportionality as a half m omega squared. It just makes the equations of motion come out with this very simple form. And the interpretation of omega then, right, it is one way to look at it is that it is the frequency, the angular frequency of oscillations in the x direction. Another way to look at it is that it gives, it's like an inverse timescale for the growth of perturbations in the y direction, right? So if you think about it, if omega is very big, right, the e to the omega t term is going to grow very quickly, and therefore the particle is just going to slide down the saddle very quickly, right? So omega gives us a measure of how quickly the particle would slide off in the y direction, and that interpretation is going to be relevant later on. So now let's start thinking about what happens when the saddle actually rotates, right? So I'm going to say the saddle is rotating with a particular angular velocity, which is going to be capital omega, right? And that's a vector. I'm going to say it's just rotating about the z-axis, right? So it's kind of going around like that, which is described by an omega vector pointing straight up aligned with the z-axis. Okay. So the equation of motion in a rotating frame takes a very specific form. I have done a video on this in the past, deriving this. For now, I'm just going to take this as a given. And the equation of motion in the rotating frame has these fictitious force terms in it, right? The Coriolis force and the centrifugal force. There's also an Euler force term if omega is not constant, but I'm going to assume that it's rotating at constant angular velocity, right? So if we construct the equation of motion in general, it looks like this. Mass times acceleration, so r double dot second derivative of position, is equal to the force acting on the particle. Then we get a minus 2m omega cross v term, or v is the speed, so I can write that as r dot, right? That's the Coriolis force term. And then I get a centrifugal force term, minus m omega crossed with omega crossed with r, right? And again, I'm assuming that capital omega is a constant, and therefore there's no Euler force term in there, right? So this is our equation of motion. And I should mention one thing here, which is that it looks like a three-dimensional problem, right? Because we've got three axes, x, y, and z. The particle is actually moving in three dimensions. However, we can think of it as a two-dimensional problem, right? Because it's kind of the particle is constrained to move along the surface of the saddle. And so if we know x and y, we automatically know z, right? So it's actually really just a two-dimensional problem. And so we don't really need to think about the z coordinate. We can just think about the x and y coordinates, because if we know those, we automatically know the z coordinate, right? So the reason I'm mentioning that now is, well, if I want to know what the force vector is, right? Force is minus the gradient of the potential energy, right? So minus grad of u. We've already kind of done this when we when I talked about the equations of motion down there earlier on. But if we want to do this in vector form, right, we're going to end up with, well, m omega squared times x, right? If I take this u function of x and y and differentiate it with respect to x, the x squared turns into a 2x, and that 2 cancels with the factor of a half. Okay, and so I'm going to put a minus sign in there because force is minus the gradient of the potential energy. And then similarly in the y direction, we just get m omega squared y. So there's our force vector. And again, as I said, we don't really need to think about the z direction because it's automatically determined if we know x and y. So I'm going to think of this as a two-dimensional vector. Okay, so we've got f. Now, how can we write down expressions for the Coriolis term and the centrifugal term? Well, let's think about the Coriolis term first, because that's actually a little bit more difficult. So if we do a little bit of working here, well, if we take our omega vector and cross it with r dot, which is the velocity vector, right, we can just use our standard determinant method. So determinant of ijk, and then omega is going to be pointing along the k direction because it's aligned with the z-axis. So 0, 0, capital omega, and then r dot, right, I'm going to write that as x dot, y dot, and then just 0, because again we're thinking of this as a two-dimensional problem, right? So the z direction doesn't really matter. And if you expand that determinant, right, you'll find that you get minus omega y dot in the I direction, and then you get omega x dot in the y direction, and then you would have to multiply that whole thing by minus 2m, right, according to this equation of motion. Okay, so in fact, I'm just going to take that and move all of that over there. And then we can start putting all of these various terms together to construct our full equation of motion. Okay, so we'll talk about the centrifugal term in a moment. It's not as difficult as it looks, right? So far, if I start writing out our equation of motion in vector form, we've got m times x double dot y double dot, right? That's the r double dot vector, is equal to this thing, right? I can take out a factor of m omega squared. So m omega squared, then minus x, and then y. Then we've got minus 2m times this thing, the Coriolis term, right? So it's minus 2m times minus omega y dot, and then omega x dot. Okay. Now, for the centrifugal force term, you could go through and actually do all of these cross products. The simpler way to do it is remember that we're thinking in 2 dimensions, right? Now, we know that the centrifugal force always points directly outwards, right? And we also know that it has a, in fact, I'll write this down. It has a magnitude of m times the radius of the circular motion, r, times omega squared, right? So if we know, right, that its magnitude is mr omega squared, and we know that it's pointing straight outwards, we can actually immediately write down the centrifugal force vector as plus, it's going to be m times omega squared, and then the vector that points straight outwards with a magnitude of r is just xy, like that, right? So again, you could go through to convince yourself, you could go through and do 2 cross products. You would get exactly the same result. However, we can just use our knowledge of the direction that the centrifugal force points in to just immediately write that down. Okay, so if we just collect all of this together and write it as 2 equations of motion in x and y, what are we going to get? Well, the m's conveniently cancel everywhere. The equation that comes from comparing the top components, or the x components of all of these vectors, is going to be as follows. So x double dot, well, on the right-hand side, we're going to get capital omega squared minus small omega squared times x, right, from the first vector and the third vector. And then from that middle vector, we get a plus 2 capital omega y dot. So there is one equation of motion. Now, the second equation of motion for y is going to be y double dot. Again, we get capital omega squared. This time we get a plus small omega squared because there is no minus sign there. So plus small omega squared y. And then there's another sign difference here. I get minus 2 omega x dot. And there are our 2 equations of motion that describe how x and y vary with time. So now on to actually solving them. Well, these are both second order differential equations. And so we could do our usual thing of just guessing a solution, right? So the usual form of the solution to guess is an exponential, right? Because if you choose, I'll write this down actually. So if you try a solution of the form where x is some constant x0 times e to the lambda t, lambda is some constant that we have to determine, and y is also some constant y0 times e to the lambda t. The first and second derivatives of x and y will all be proportional to each other, right? Because when you differentiate an exponential, you just get back something proportional to the original function, right? So if all of these time derivatives are proportional to each other, you could choose lambda in exactly the right way to make sure these 2 equations are satisfied. So all we're going to do is plug those trial solutions into the equations and see what we get for lambda, or see what equation lambda has to satisfy. So let's go ahead and do that. So remember that if you differentiate either of these terms, basically all you do is you pull down a factor of lambda. If you differentiate twice, you pull down a factor of lambda squared, right? So what that means is these double dotted x and y terms are just going to be lambda squared times x and lambda squared times y. Similarly, these terms here, y dot and x dot, are going to be lambda times y and lambda times x. And so I'm going to collect all of the terms onto the same side. If we look at the upper equation first, right, the x double dot is going to turn into lambda squared x, right? I'm just going to leave it as lambda squared now. And I'm going to collect all the x terms together. So I'm going to put some brackets there. So lambda squared, if we take these terms, right, big omega squared minus small omega squared, and move those over to the other side, we're going to get plus small omega squared minus big omega squared, right? And then I can factor out an x. Now, there's also this y dot term. I want to take that to the other side, so I'm going to have to change its sign, and it gets an extra factor of lambda because it's been differentiated with respect to time. So I'm going to get minus 2 big omega lambda y is equal to 0. Now, I can also take advantage of the fact that x and y are both proportional to the same function, right? So x is really x naught e to the lambda t, y is really y naught e to the lambda t, and so I can just cancel down the e to the lambda t parts because that's not 0, right? And just write x0 there and y0 there. Okay, now we've got one equation here that links together lambda and x naught and y naught. If we go through a very similar procedure, right, with the y coordinates, you'll end up with something that looks similar, just with some sign differences. It's going to be lambda squared minus small omega squared minus big omega squared times y naught, and then we're going to get a plus 2 omega lambda x naught is equal to 0. Now, let's think about what this pair of equations actually implies for lambda and x naught and y naught. And I think the easiest way to do this is actually to use some linear algebra and write this down as an equation involving a matrix, right? So I'm just going to write down some big brackets, and we can think about what goes into this matrix in a moment. And it's going to be some matrix times the vector x naught, y naught is equal to the 0 vector, right? Combining those two equations together. Now, to figure out what entries go into this matrix, right, basically it's just the coefficients of x naught and y naught in the top equation and the bottom equation, right? So, for example, the top left entry is going to be this term here because that's the coefficient of x naught in the upper equation. I'm going to write that as lambda squared. I'll just reorder the terms actually. Minus big omega squared plus small omega squared, right? And then the coefficient of y naught is minus 2 times big omega times lambda, and so I put that there. And similarly, right, the coefficient of x naught in the lower equation is 2 times omega times lambda. The coefficient of y naught is lambda squared minus omega squared minus omega squared. Okay, now the reason why this helps is because this kind of reveals that there are two possible solutions. One is that this matrix has an inverse, then we pre-multiply both sides of the equation by that inverse, and we find that x naught is 0 and y naught is also 0, right? Because if we can invert that matrix, that would imply that this vector of x naught and y naught would also be 0. However, it's a perfectly valid solution. It's just not a very interesting one, right? It's just the particle is always sitting exactly at the origin. So if we want to figure out the more interesting case, we have to consider what happens when the matrix is not invertible, right? Because then we get non-trivial solutions. Now, the condition for a matrix to be not invertible is for its determinant to be 0, and its determinant is that thing times that thing minus that thing times that thing, right? So we could use that fact that the determinant is 0 to set up an equation for lambda, and then we'd be able to solve it and get the specific values of lambda that give us non-trivial solutions, right? Now, the reason why I reordered these terms is because, well, when we do the upper left term times the lower right term, this actually looks like a difference of two squares type thing, right? Because you've got lambda squared minus big omega squared plus small omega squared, and then lambda squared minus big omega squared minus the same thing, small omega squared. And so when I multiply those two things together, I can use our difference of two squares identity to write that as lambda squared minus big omega squared all squared, and then minus omega to the power of 4, all right? So that's the upper left term times the lower right term. And then from these other two terms, we are going to get basically just plus 4 omega squared times lambda squared, right? It's a plus because when you times them together, you get a negative number, or you get a minus sign, sorry. But then the determinant is like you have to subtract off the product of those two things. So we get two minuses and we get a plus overall. Okay, so that is supposed to be equal to 0 for the matrix to be non-invertible. So it's a polynomial that we could solve for lambda. Let's do that. We're going to have to expand the brackets. If we expand the brackets, we get a lambda to the power of 4 term, right? Then we get 2 lambda squared times big omega squared. Or really, it's minus 2 times lambda squared times big omega squared. But then we've got plus 4 of the same term there. So we've got minus 2 of it, plus 4 of it. So we have plus 2 of that thing overall, right? So plus 2 big omega squared times lambda squared. And then, again, the third term that we get when we expand those brackets is going to be plus big omega to the power of 4. But then we've also got our minus small omega to the power of 4 there. And then that is supposed to be 0. Now, this actually kind of factorizes very nicely because this stuff here is a perfect square. This is just equal to lambda squared plus big omega squared, all squared, right? So that takes care of the first 3 terms. Then we've got this little omega to the 4 left over, which I'm going to put on the other side, right? So all of that squared stuff is equal to small omega to the power of 4. And then if I just manipulate that a little bit to get lambda squared on its own, we find that lambda squared would have to be, taking the square root of both sides, it would be minus big omega squared plus or minus small omega squared, right? So we end up getting 4 different solutions for lambda because there's a plus or minus here, but then when you take the square root to get lambda itself, you'd get another plus or minus. So there are 4 different values that we could get in total for lambda. So now what I want to do, now that we've found our values for lambda, is think about physically what do those various different values of lambda actually mean? What type of motion do they correspond to? And essentially, it's going to depend on the relative sizes of big omega, right? Which remember was the angular velocity of rotation of the saddle. It's going to depend on the size of that relative to small omega, which was this parameter that defines the curvature of the saddle and basically tells us about the time scale of the motion in that saddle in the case of no rotation, right? And so the first case I would like to consider is what happens if big omega is bigger than small omega, right? In that case, right, you're taking this negative number minus omega squared, minus big omega squared, and then whether you add or subtract small omega squared, it's always going to be negative, right? Because that first term has a bigger magnitude than the second term. So whether or not you add it or subtract it, you always end up with a negative number for lambda squared, right? So that means lambda squared will be less than 0 always, right? Now, if the square of a number is less than 0, then the number has to be imaginary, right? And so lambda is going to be imaginary in this case. Now, remember, if you think back to our trial solutions, x naught e to the lambda t, y naught e to the lambda t, if lambda is actually an imaginary number, we get e to the power of I times something times time. And that is that's an oscillating term, right? Because e to the I times something is related to cosines and sines, right, of the exponent. And so in this case, we find that x and y always oscillate, right? So I'm just going to make a note of that. So x and y have oscillatory solutions. Okay, so what about the other case? If big omega is smaller than small omega, right, then it's going to depend on whether you take the plus sign or the minus sign, right? Of course, if you take the minus sign there, then you always end up with a negative number. However, if that second term has a bigger magnitude and you add it on, you get a positive value, right, for lambda squared. So I'm going to say positive values of lambda squared exist. So the lambda squared values are not all positive, but some of them are positive, right? Now, what does that mean? Well, you get some oscillatory parts of the motion, but you also get some which are just exponentials, right? And so for the values of lambda squared that are positive, you get real values of lambda, because you can just take the square root of a positive number and you get a real number. The two real values of lambda would be plus or minus, because remember, we have to take the square root of that whole thing to get a positive value and a negative value. We get plus or minus the square root of small omega squared minus big omega squared, right? Those would be the real values of lambda. You would get some imaginary ones as well from the minus sign, but there you go. Okay, now the interesting thing here is the plus case, right? This basically gives you a growing mode in x and y, right? So because of the existence of this positive lambda, right, you find that your coordinates actually grow in this case, or at least part of the solution grows exponentially in this case, which means that the coordinates will just grow very quickly, and therefore the ball will basically just roll off the saddle, right? Or the particle, sorry, will just slide off the saddle. And so we would say that's an unstable type of motion. And so essentially what we've said, right, is if the rotational frequency of the saddle is bigger than this critical value, then the particle will stay like it will stay on the saddle and it will just kind of oscillate, right? Whereas if it's not rotating quickly enough, in the second case, if the saddle is not rotating quickly enough, then it'll just fall off the saddle, right? So you have to rotate it faster than this critical frequency if you want to keep the particle on the saddle. Now, we can understand that in terms of timescales, right? Because remember, I said that small omega is basically a number that tells you about the timescale of the motion on the saddle in the absence of the rotation, right? So what these conditions actually mean, right? These two conditions here, is that in the first case, right, when big omega is bigger than small omega, that's saying that the saddle rotates on a quicker timescale than the motion of the ball, or sorry, of the particle within the saddle in the absence of rotation. In other words, if the particle tries to slide off, the saddle will rotate, right? So if it starts sliding off in this direction, then this part of the saddle that curves upwards can just rotate and stop it from falling down in time. Like it has enough time to do that. It rotates around quickly enough to stop it from sliding off. However, if big omega is smaller than this small omega, which defines the timescale on which it falls off, then the saddle doesn't spin around quickly enough. It doesn't kind of stop it from falling off, and it just falls off. So there's the interpretation of that. So the last thing that I'd like to talk about in this video is a limiting case of the motion in which the saddle rotates very, very quickly, right? So we've already considered at the very beginning of the video, we've considered what happens in the case where big omega goes towards 0. In other words, the saddle stops rotating, right? What about the opposite case? So we are going to make an approximation. We're going to say, consider the case where big omega is much bigger than small omega, right? In that case, if you look at this equation for lambda, the parameter that goes into our solutions for x and y, right, we can neglect that plus or minus small omega squared term, and we would conclude that lambda has to be equal to plus or minus I times big omega, right? In other words, lambda is purely imaginary. We can go one step further and use this equation, right, just above there, to work out a relationship between x0 and y0. You could alternatively use that one, but you would get the same result. I think the algebra is a little bit easier if we use the middle one there. So let's do that. Now, if we plug in lambda equals plus or minus I omega, then what's going to happen? Well, again, we can neglect this term in the middle, the small omega squared, right, because we're considering the limiting case. Then we know that lambda squared and minus omega squared, minus big omega squared, are actually equal. And so that first term would become minus 2 big omega squared times y0. The second term is going to be plus or minus 2i omega squared x0 is equal to 0, just by substituting this lambda equals plus or minus I omega, right? If you rearrange that to get the ratio of y0 to x0, you'll find right, this should technically be approximately equals, you'll find that this is approximately equal to plus or minus I. So what does that mean? Well, remember that I is actually the same thing as e to the I pi over 2, right? So that is e to the plus or minus I pi over 2. And when you multiply a complex exponential by a term like this, right, that's equivalent to a phase change, right? So what this means is that y and x are oscillating with a phase difference of pi over 2. Okay. What does that mean? Well, they're oscillating with the same angular frequency, right? Because lambda is plus or minus I omega. They're both oscillating with a frequency of big omega, but they're pi over 2 out of phase. Now, if you think about it, that just means that the particle is moving in a circle with angular frequency big omega, right? That's exactly what circular motion is. It's just two perpendicular, simple harmonic motions, which are pi over 2 out of phase, 90 degrees out of phase. So I'm just going to write down that that is circular motion at an angular frequency of omega. This is in the rotating frame, remember, right? Then if we were to transform back to the lab frame, like imagine we're in some lab actually rotating a saddle around with a particle in it, what would that look like in the lab frame? It would actually just be stationary because you'd be subtracting off that rotational motion to transform back into the lab frame, right? So your particle would actually be stationary in the lab frame, which is interesting. It actually makes a lot of sense though, right? Because if it's rotating really, really quickly, the effects of the upwards curving part of the saddle and the downwards curving part of the saddle will average out. They'll cancel each other out, right? If it's rotating very, very quickly, it'll be pushed, it'll kind of try to fall outwards at one moment, but then very quickly the next part of the saddle will rotate around and give it a push back. And it'll just be getting these kind of pushes in and out very, very quickly. And overall, the effect is that the potential of the saddle just averages out and the particle just ends up sitting there. So anyway, there you go. I hope this has been interesting. I do think this is an interesting system, and I will see you again soon.